Hello everyone. Today we're going to be completing our study of trigonometry, at least in the Algebra 2 class. Next year, during either pre-calculus or trigonometry, you'll be going into this topic in more depth. This will cover section 7.4, which we'll start graphing sine and cosine. We'll skip 7.5, which involves graphing tangent, and you'll see that next year. And then we'll go on today to section 7.6, where we'll be performing some additional transformations on the sine and cosine graphs. Okay. As you can see here, we are going to be looking at various attributes of the sine and cosine graphs, including the period, the midline, and the amplitude, and looking at those in general for any periodic functions, and then specifically graphing sine and cosine. As you'll notice here, a periodic function is a function that repeats in a regular pattern at a regular interval, and that regular interval is called a period. This would be, for example, you probably have seen in science classes, waves of light or sound, that sort of thing. Those are periodic functions. So what we're going to do first, before we describe the period, the midline, the amplitude, the max, and the min, I'm going to sketch just an example of a generic periodic function. Okay, so I'll label this axis, just counting by ones, but I'll label every other, 0, 2, 4, 6, 8, 10 on the x-axis, and 0, here I'll label -2, and then 2, 4, 6, and so on. Okay, and of course -2 over here. So I'm just going to make a wave function, and this function that I'm going to draw looks very similar to what we're going to see when we graph sine and cosine. So I'll just put a point here at -2, 2, a point at 0, 0, a point at 2, 2, a point at 4, 4, a point at 6, 2, a point at 8, 0, and another point at 10, 2. And I'll just connect those with a curvy graph, okay? And I'm purposely doing this not because we can't see periodic functions with pointy graphs. It's just that we want to practice drawing a smooth curve because that's what we're going to see when we draw sine and cosine, okay? So the period is the horizontal distance, in other words, the distance from side to side, required for the graph to complete one repetition or cycle. Okay, so if we look over at the graph, what I'm going to do is I'm going to draw a rectangle. And I'm going to use the highlighter to draw a rectangle. I'm going to draw the left side of the right rectangle here and the right side of the rectangle here. And you'll notice I put those vertical lines passing right through 2 points that both represent the lowest points on this graph, the minimum, okay? And in general, if we are looking for the period, if we just look for points on the graph going from one minimum to the next minimum, or for example here, one maximum to the next maximum, that would represent one cycle or one repetition or one period. Okay, so I'll just complete this rectangle here. Okay, now the midline is a horizontal line between the minimum and maximum points of the graph. Okay, so I'm going to go ahead and I'll draw that horizontal line here. So here's that horizontal line. And that horizontal line would be called the midline. And the equation of that line here is always going to be a y equals line. It would, of course, in this particular case, be y equals 2. Okay? The amplitude is a distance. Okay? So the amplitude is the distance from the midline to either the maximum height of the graph or the minimum height of the graph, okay? In other words, it would be half the height of the rectangle. So for example, right here or right here, here or here would represent the amplitude, okay? And when we look at the equation for these periodic functions, sine and cosine, that amplitude is going to be represented by A. And it's actually always going to be represented as the absolute value of A, because A sometimes will, in the equation, be negative. For example, if the graph is reflected, it's the letter A that we've used before to represent vertical stretch or shrink and also reflection. So we know it can be negative, but amplitude is a distance, and so it's positive. And so we can see in this case here, the distance between the midline and the max is 2 units. The distance between the midline and the min is 2 units. So the amplitude in this graph is 2 units. Okay, so we'll define that. So the distance from the midline to the max or min value of the graph. And it's always positive. Okay? Now, because of that, let's potentially say that you didn't have the graph right in front of you, but you knew what the midline of the graph was, and you knew the value of the amplitude. There's a very easy equation or formula that you can use to calculate the min or max value of the graph. Very, very straightforward. So the maximum value is always going to be the numerical value of the midline, which in this case would be 2, plus the value of the amplitude, which in this case is 2. And sure enough, you can see the max here is going to equal 2 plus 2, or 4. Okay? So it's equal to the midline plus the amplitude. And we said in this particular case, it's 4. In general, though, it would just be whatever the midline or the amplitude would be for that particular case. Okay, so then we're going to have here the midline minus the amplitude will give us the minimum. So of course, in this particular case, we have the midline is at 2, the amplitude is 2, 2 minus 2 gives me 0, and sure enough, if we look at the graph, the min is equal to 2 minus 2, or 0. Okay? So we're going to look now specifically at the graph of the sine function. To help us figure out what coordinates are going to be on that graph, we're going to use the values we know about the sine of typical radian values on the unit circle. Okay, so let's look at the unit circle first. We remember, of course, that the unit circle has a radius of 1 unit. Okay, so the radius here is equal to 1. And of course, you know, I could draw another radius up here. That would be 1 unit, and so forth all around the circle. Okay, so at the center, of course, of that circle is the point 0, 0. Going to the right, I'm at 1, 0. Going up 1 unit, I'm at 0, 1. To the left 1 unit at -1, 0. And down 1 unit at 0, -1. Okay? Now, as you can see here, the variable we're using to represent the radian measure in this particular case is x. So x is the measure of the angle in radians. Rather than using theta here, we're using x. And so we know from what we have learned prior in this chapter that on the unit circle, the x value of a coordinate is going to be the cosine of the angle measure. So we can say x, or the x value 1 here is going to be the cosine of x, and the y value is going to be the sine of x. Okay, and that of course is going to be true throughout the circle. For every coordinate, the x value will be the cosine and the y value will be the sine, right? And so when we're looking for the information that we need for our table here, what we're looking for is for a given radian measure, which is x, we're taking the sine, for example, of 0, the sine of pi over 2, and so on. That will give us the y value, okay? So for each of these values, we're looking for the sine of x. So the sine of x here is going to be the y values of these coordinates, okay? Now to graph, we're going to make this very simple. To make a typical parent sine graph, we're just going to use the sine values at the corner angles, okay? We're not going to worry about the acute angles in between, just to make a general curve. Now, to label these values, we'll go ahead and do that. Let's remember, we're going to be labeling here in radians. We're not going to worry about degrees. So we're going to have 0 radians. Here we'll have pi over 2 radians. Here will be pi radians. Here will be 3 pi over 2 radians. Okay? And finally, of course, we can also call this point 2 pi radians. Now, as you'll notice, we have some negative radian measures as well. And so we'll also want to label the negative radian values. So rotating clockwise here, we'll be at negative pi over 2. Another quarter of the circle will be at negative pi. Another quarter of the circle will be at negative 3 pi over 2. And finally, full way around the circle will be at negative 2 pi. Okay? Now we can fill in, using the information we have on the unit circle, we can fill in the values in our table. Okay? I'll start with the positive values. So for 0 radians, we can see that the sine of 0 is going to be 0. And so we can fill that in. The sine of pi over 2 is 1. The sine of pi is going to be 0. The sine of 3 pi over 2 is negative 1. And the sine of 2 pi is 0. Okay? Let's go in the other direction. Let's go clockwise to the negative radian values. At negative pi over 2, the sine will be negative 1. At negative pi, the sine will be 0. At negative 3 pi over 2, the sine is 1. And at negative 2 pi, the sine is 0. So what you'll notice here is this periodic cyclical pattern, this repetition, 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0. So we have a pattern that repeats over and over and over again, okay? And specifically when we're going to be graphing and we're going to be doing transformations, what I would like you to focus on for the parent table for y equals sine of x, I want you to look at the positive radian values and also 0, okay? We'll be using some negative sometimes, but focus on these 5 key X and Y values. So we're always going to be looking at 5 key coordinates to help us graph, whether it be with the parent or the transformed. We're always going to be graphing at least those 5 points, okay? So we'll say that this is the parent of all sine graphs, okay? All right, so let's make a sketch of what we've just drawn. And you'll notice here, I have coordinate plane here. You know, here's the x-axis and here's the y-axis, but there's no graph paper. And because, you know, what we're graphing here is very, very simple. You know, we basically are going to have, as you can see, that as far as the y values here, we just have 0 and we have 1 and we have -1. And that's it. Okay. And then, of course, for the x values, we've got 0 and 2 pi. We have pi. We have pi over 2. And we have 3 pi over 2. Okay. 1, 2, 3, 4, 5 key values there. Okay. So in addition here, just to emphasize to you that the graph does continue because we can rotate clockwise and go to negative radian values, that we can go to -2 pi or beyond, right? This graph is going to continue forever and ever and ever in both directions. We know that we can keep rotating, right? -2 pi, -4 pi, -6 pi, -8 pi, and keep going and going and going forever. So we have -pi here, -pi over 2, and -3 pi over 2, okay? And so what we're going to do is we're going to plot these coordinates, just that we, you know, the coordinates that we have in our table. Very, very straightforward. So when x is -2 pi, y is 0. When x is -3 pi over 2, y is 1. When x is -pi, y is 0, and so on. I'm just going to copy right off the table and copy it right onto my graph, okay? And you're going to see how this pattern is like a wave that just keeps repeating itself. Okay, and so let's draw the curve. Okay, and the one thing you want to notice here to kind of help you relate this to what we learned above is what the amplitude of this graph is and what the period of this graph is. Okay, so for the parent function, y equals sine of x, okay, you want to notice here that if I were to draw this rectangle in the same manner that I did above, okay, what I can do is I can draw a rectangle, and I can do that right around one cycle of the graph, okay? So just like this. Okay, now you'll notice, you know, above I had said, you know, when you draw a period, an easy way to do it is to go from minimum to minimum or maximum to maximum. But also here, you can see how I did it here. I noticed, for example, that, you know, at 0, 0, we're at the midline and the graph is increasing, right? So where does that happen again? If we continue along the graph, at 2 pi, we are at 0 and the graph is increasing, and we know that's where the pattern continues. I could have drawn this rectangle in other places as well, though. For example, I could have drawn, you can see that at -pi over 2, we're at -1. The next time that happens is at 3 pi over 2. Okay, and what you'll notice is 1.5 pi plus another pi over 2 is 2 pi. So if I had drawn from 3 pi over 2 to -pi over 2, I would have had that same period, 2 pi. No matter where I start, the cycle is going to be 2 pi, okay? All right, so for y equals sine of x for the parent, the period is going to equal 2 pi. And you can see that the midline right here, the midline is at y equals 0. And you can see the amplitude, whether we look here or here, the amplitude is going to equal 1 unit. Okay, so that's for the parent sine function y equals sine of x. Okay, that's going to be true also for the parent cosine function as well. Okay, so here's a typical equation. This is the equation, the formula we would use when we don't have any horizontal or vertical translations. That we'll see when we get to section 7.6. And so you can see here how this fits in. Y equals sine of x. In this case, you can see for the parent, a equals 1. And for the parent, b is equal to 1. So what is b in this case? Well, b is a way of calculating the period. Okay, so let's look at that. Well, first of all, we know the amplitude is the absolute value of A. We've talked about that. But the period is calculated by taking 2 pi and dividing it by B. Okay? Now, we already said for the parent sine of x, the period is 2 pi. And so you can see B is equal to 1. If we take 2 pi and divide it by 1, we certainly get 2 pi. Okay, and so we can make a note of that. You know, for the parent, the period is equal to 2 pi over b, which is 2 pi over 1, which is 2 pi. Okay. Now, another thing to notice for future is that in certain situations, you're going to be given the period or given the amplitude or both and be asked to write an equation from it. And so from the period, you might have to calculate the value of b, basically working backwards. So understand that what we really have here is an equation. The period is equal to 2 pi over b. Well, you know from your understanding of algebra that if I have a variable here, the period, and I have the variable here, b, if I interchange those, the equation remains the same, right? So these two could change locations algebraically. So another way of writing this formula would be to say that b is equal to 2 pi divided by the value of the period that we're given. Okay, so if you're given a situation where you're given the period and you need to calculate b, this is would be the way you can do it. And you can see it works for here, right? The period is 2 pi over 2 pi is equal to 1. Okay. One more thing to notice before we move on is just the general shape of the sine curve and characteristics of the sine curve, because we're also going to be looking at the cosine curve, and you want to be able to distinguish between the sine curve and the cosine curve. Okay, so one thing to notice here for the parent sine function, okay, between 0 and 2 pi, the general shape here is that of a hill on the left and then a valley on the right. So between 0 and 2 pi, it looks like a hill and then a valley. Okay, and of course, if the graph were reflected, it would be the other way around, right? You'd have the valley and then the hill if you reflected it over the x-axis. Okay, another thing to notice, to kind of go back a number of months when we were studying odd and even functions, you may remember that an odd function is one that has rotational symmetry about the origin. In other words, if you rotate it 180 degrees, the graph looks identical. So let's do that. I'm going to rotate the paper 180 degrees, and you will notice that the graph looks identical to what we had to begin with. Okay, so another characteristic that's important for you to recognize as well is that we have y equals the sine of x and all of its transformations, where, basically y equals the sine of x is going to be an odd function, which means it has 180-degree rotational symmetry about the origin. Okay? We're going to look now at how amplitude affects the sine curve, and then after that, we're going to look at how period affects the sine curve. Okay? And also, one thing to notice as well is that what we're looking at here with sine would apply also to cosine. Okay? So, for example here, let's just start with the parent. Okay, and remember I told you we're going to use 0 and the next 4 positive radian measures that are the corner angles on the unit circle as our typical parent table. Okay, so basically we'll have 0, pi over 2, pi, 3 pi over 2, and 2 pi. And then 0, 1, 0, -1, 0 would be our 5 key points there. Okay? So let's go ahead over to this graph. What we're going to be doing is graphing this function as well as 3 transformations of it where we are going to first vertically stretch the graph, then vertically shrink the graph, and then reflect the graph and see how that affects the graph. Okay, so let's just label this. I'll label this 0, 1, 2, 3, and -1, -2, -3 on the y-axis. On the x-axis, we'll break up what we are given here evenly. So we've got 2 pi here, pi over 2 here, and 3 pi over 2 here. Okay, and so I'm just going to plot the points in my table. So I've got 0, 0, pi over 2, 1, pi 0, 3 pi over 2, -1, and 2 pi 0. Okay, and I'll just sketch that curve. And there's my parent graph. Okay. Now, what you want to notice for this graph before we keep going is that, as we already said, the amplitude is going to equal the absolute value of A. Now, in this case, A is just positive, so I'll just say A equals 1. Okay. And in general, you want to look at what the pattern is here. So basically, you start off the graph at 0, then the graph goes to a max, then back to 0, then a min, and then to 0. So you're basically at 0, max, 0, min, 0. Okay, that's the general pattern here. Another thing to notice is this graph can keep going and going and going forever and ever, because if you think about it, this is just a model of the circle. Okay, if you just kind of think of the unit circle as like a bicycle wheel, just rotating, 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 and rotating, I can successively rotating it multiple times. So I can go 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, 12 pi, and so on. Or -2 pi, -4 pi, -6 pi, -8 pi. So the arrows here are very, very important. You want to notice that. And because of those arrows, we need to recognize that the domain is going to be all real numbers. And the domain is going to be all real numbers for sine and cosine, regardless of how we transform the graph. Whether we stretch it, shrink it, reflect it, translate it, shifting it left, right, up, down, that is going to be the domain regardless. Okay? Now the range will depend on specifically how we transform the graph. So in this case here, the range is going to go from our minimum here, which is at -1, up to our maximum, which is at 1, including those points. So -1 is less than or equal to y is less than or equal to 1, but we know that in interval notation, that would just imply brackets, and we write it just like this, and that would be the range of this function. Okay? All right, so let's go on and let's do the same for y equals 3 sine of x, okay? Here, the amplitude is equal to a is equal to 3, and we know that this is going to be a vertical stretch by a factor of 3. Okay, so when we make the table here, we're going to use the parent table, of course, as a reference, and we're simply going to multiply the parent y values by 3. And so you see when we're graphing, we're doing very much what we've done before in order to transform graphs. And so just multiplying these y values will now give 0, 3, 0, -3, 0. Okay? On the other hand, the x values will remain the same as those of the parent. So we'll have 0, pi over 2, pi, 3 pi over 2, and 2 pi. That will not change. Okay? So let's go ahead and graph what we've got here. We've got 0, 0, pi over 2, 3, pi 0, 3 pi over 2, -3, and 2 pi 0. Okay, and so sure enough, you can see how that amplitude change is affecting the sine curve. We've vertically stretched that graph. And on the other hand, the domain has remained the same, right? It's still all real numbers, no change there, okay? The range now goes from the minimum -3 to the maximum 3. Okay? All right, so let's look at y equals 1/3 sine x. Okay, now for any of these, if you want to pause and try this on your own, feel free, of course, to do that, because I would presume many of you at this point would probably be able to do both C and D on your own and just check it from my work. Okay? All right. So, of course, here we have an amplitude of 1/3. And we have a vertical shrink by a factor of 1/3. So of course, we're going to multiply the y values of the parent by 1/3. Okay, and so taking the original values here, multiplying them by 1/3, we now have 0, 1/3, 0, -1/3, 0. Okay. On the other hand, the x values still remain the same. 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay. So we're here at 0, 0. Pi over 2, 1/3. Well, here's 1, here's a half. So here's a third, about, right? Pi 0, 3 pi over 2, -1/3, and 2 pi 0. Okay? So you can see we've got the same shape, it's just vertically shrunk. Okay? The domain still is all real numbers. And the range is going from -1/3 to 1/3. Okay, you can also see that just by looking at your table. Okay, finally, we're going to look at reflecting the parent graph. Okay, so we see here that we have A here is -1. Okay, so that's important to recognize that. Notice here that A is equal to -1. Now remember, the amplitude is going to equal the absolute value of A. So the absolute value of -1. So the amplitude is still 1. And it's very important that you notice that. Amplitude is always positive because it's a distance. Okay? So in this case here, you can see, let's look at this. We make the table. We're going to be multiplying the parent y values by, as you can see with that negative sign, -1, right? So we're just going to end up taking the same y values just with the signs flipped on the ones. So 0, -1, 0, 1, 0, and the x values will remain the same. 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay? So I'm going to go up and graph those. Okay? So we've got 0, 0, pi over 2, -1, pi 0, 3 pi over 2, 1, and 2 pi 0. Okay? So when I make the curve here, what you'll notice, if you compare the red graph, which is the parent, to the blue graph, which is the reflection of the parent, but with the same amplitude, they're just reflections of each other over the x-axis. Okay, and another thing to notice that's important is, remember we had said that the sine curve between 0 and 2 pi, you're going to see a hill and then a valley, and of course when you reflect the graph, you're going to see a valley and then a hill. Okay, so that's important to notice. Okay, so you'll notice that when we reflect it, we have a reflection over the x-axis. So basically, you're going to see a valley and then a hill. Okay, and also something to notice here is that, remember here we said your pattern for, we have 0, max, 0, min, 0. Okay, and that's true for every one of these A, B, and C, right? So that 0, max, 0, min, 0 is going to be true for A, B, and C. But then when we reflect, now we've got the opposite. We've got 0, min, 0, max, 0 right here, because it's reflected. Okay? And something, of course, I don't want to leave out, just because you reflect doesn't mean you're changing the domain. So the domain is still all real numbers. And the range is still going from the min to the max, right? So the min is -1, the max is 1. So the range is going to be the same as that of the parent in this case. So the range is going to be from -1 to 1. Okay? So we're going to go on now, and we're going to see how changing the value of B affects the graph. We're going to look now at how the period affects the sine curve. And what you want to remember is that the period is based on the value of B. Okay? And so here is B, because if we remember the formula, we have y equals A sine of BX. Okay? So B is 2/3 in this particular case. Okay, now we can notice here, if we want to first determine the amplitude and the period, the amplitude you can see is A equals 1. So the amplitude is the same as that of the parent. So the only feature we're changing here is the value of b, so we are changing the period, okay? Now, the key that you want to remember is that the period is found by taking 2 pi, the period of the parent, and dividing it by the value of b. So if we do use this formula, we have 2 pi divided by 2/3. Now remember, of course, when we divide by a fraction, that's the same as multiplying by the reciprocal. So dividing by 2/3 is the same as multiplying by the reciprocal, right? We're just doing keep, change, flip, multiplying by the reciprocal. And so what's going to happen is, of course, the 2 will cancel. And so the period is going to equal pi times 3, or 3 pi, okay? So what that indicates immediately is that the period is longer than that of the parent, which means we're stretching that graph out right to left. And so we're going to end up here with a horizontal stretch. We can tell that this is going to be a horizontal stretch because the period is larger than that of the parent. And we'll look in a moment at how we can describe that horizontal stretch after we've graphed it, okay? So what we're going to look here in step 2 is we're going to find the 5 key x values for the graph. So the key here also is because of that change in the period, whereas before, when we were just looking at a change in amplitude, the x values stayed the same, and we were just changing the y values to vertically stretch or shrink or reflect. Now we're going to be changing the x values because we're going to be horizontally stretching or shrinking the graph because we're changing the value of b. Okay, so let's remind ourselves of the parent, y equals sine of x, and its equation, which we're going to use to help us transform and horizontally stretch the graph. Okay, so we know we've got 0, pi over 2, pi, 3 pi over 2, and 2 pi, and 0, 1, 0, negative 1, 0. Okay, now let's look at the transformed graph. Okay, and that transformed graph, of course, is y equals sine of 2/3 x. Okay, so in this case here, we are just horizontally stretching the graph here, and therefore we haven't changed the amplitude from the parent. It's still 1, and so we're going to leave the y values alone. 0, 1, 0, negative 1, 0. And what we're going to change are the x values. Okay, so I'm going to show you 2 different ways that you can do this, and you can decide which method that you prefer. Okay, I'm going to show you what I feel is the simplest way first, but you might find the other way works for you better, so you just decide what makes it easiest for you. Okay, now we know that the period here of our transformed graph is 3 pi. Okay, so instead of going from 0 to 2 pi, we're going to go from 0 to 3 pi. And we're going to still break the graph up into even increments. So if we divide 3 pi by 2 to get the point exactly in the middle, we would be at 3 pi over 2. Okay? And of course, if I divide 3 pi over 2 by 2, we know that a half of a half is a fourth. That would give us 3 pi over 4. Okay? So then you might wonder, well, then how do I get this value? Well, notice that what we've divided up into here are increments of 3 pi over 4, because watch, these all have to be the same distance apart. If I go from 0 to 3 pi over 4, I've gone 3 pi over 4 units. If I go from 3 pi over 4 to 3 pi over 2, I've got another 3/4 pi, right? 3/4 plus 3/4 is 1.5 or 3/2. And then if I want to go to figure out what this x value is, what I can do is very simple, okay? I can say 3/2 pi plus 3 pi over 4, and that'll give me this missing value. So if I want, I can find the LCD to figure this out. Of course, the LCD would be 4. 2 times 2 is 4. 3 times 2 is 6. So I have 6 pi over 4 plus 3 pi over 4, which tells me that that missing value here is 9 pi over 4. Okay? Now that's the way that I normally do it. Okay? But I want to show you an alternative that some people prefer. If what I've found in the past, some students will prefer to do it this way, and that's fine. Whichever way works for you helps. And the other method uses the parent more. Okay, and what you may want to do is after I show you the other method, rewind the video and go back and check out the first method and the second method and decide for yourself which one works better for you. Okay, what you'll notice that we did up here, okay, for a value of 2 pi, to get 2 pi to 3 pi, we divided by 2/3, or the same would be multiplying by 3/2. Okay? So what I did is I multiplied by the reciprocal of b. Okay? Or if you want to say this way, another way to do it other than the method I showed you over here is to divide the parent x values by b, which is equal to 2/3, which of course equals multiplying by the reciprocal 3/2. Okay? So watch. 2 pi over 3 times 3/2 gave us 3 pi. Okay? If I do the same thing, let's say I go over here, I'll just put a star by it so you can see it. 3/2 pi times 3/2 does give me 3 times 3 is 9 pi over 2 times 2 is 4. Does give me 9 pi over 4. Pi times 3/2 does give me 3/2 pi. Pi over 2 times 3/2 does give me 3 pi over 4. And 0 times, of course, 3/2 gives me 0. So many students do prefer just taking the reciprocal of b and multiplying every parent x value by that to get the transformed x values. Okay, so you have two options. Do that, or the first method I suggested, which is just divide up the 3 pi units into 1, 2, 3, 4 intervals. 1, 2, 3, 4 equal intervals, whichever works for you. And again, you might want to go back and just see and decide for yourself which one works better. Okay, so we're going to label the graph now, and we're going to graph the transform function. I'm also going to dash the parent to help you visualize that horizontal stretch. Okay, so we've got for the transformed function, I'm going to just label the graph. We've got 0, 1, and -1 is all I need because the amplitude is just 1. And I'm going to go from 0 to 3 pi. That's what I'm breaking this up into based on this table, right? And in the middle, I have 3 pi over 2. Halfway between 0 and 3 pi over 2 is 3 pi over 4. And halfway between 3 pi over 2 and 3 pi is 9 pi over 4. Okay? And then I'll just plot those points. So I've got 0, 0, 3 pi over 4, 1, 3 pi over 2, 0, 9 pi over 4, -1, and 3 pi, 0. Okay? So I'll just make that curve. Okay. Now, at first glance, you can see why it's so important to label your axes, because I can't tell that this isn't the parent unless I look at how I labeled the axes, that I'm not going from 0 to 2 pi, I'm going from 0 to 3 pi. Okay, so labeling your axes is going to be very important. Now, obviously, this year, because of the online format, and you're doing your assignments on Pearson Realize, you're not going to have that practice that you would have had if we were in school. So keep in mind that next year, when you're in your next math class, pre-calc or trig, that's one of the important features that you're going to have to be careful of, is make sure you're labeling the axes very carefully in order to distinguish between parent and transform functions. Okay, so now if we just in red, I'm going to dash the values of the parent so we can kind of compare this curve that we've drawn to the parent. Okay, so I've got 0, 0. Now I see pi over 2, 1, and I might be like, well, where's pi over 2? I didn't label it. Okay, well, think logically here. Okay, if I look at my graph, here I've got 3/4 pi, right? So just to the left would be 2/4 pi, 1/4 pi, 0 pi. So I'm counting by 1/4 of pi, right? I could keep going and check it. 4/4 pi, 5/4 pi, 6/4, which is the same as 3/2, and so on. So right here is 2/4 pi, or pi over 2. Right? So pi over 2, 1. Then I want to know where pi is. Remember, we just said 3/4 pi, 4/4 pi. So here's pi. So pi is going to be back at 0. 3 pi over 2 I already have labeled, so that's at -1. 2 pi, well, here's 9/4. 2 pi is 8/4, so it's 1/4 to the left. So here's 2 pi, and we're back at 0 there. Okay, so let's dash that in. Now, one thing I want to emphasize to you, as I said, is these graphs have a domain of all real numbers. So the graph isn't ending there, and since I have more space on the graph, I'm going to just continue it. And so think about what comes next, right? If you're thinking about this in terms of pi over 2, for example, of the unit circle, 2 pi is 4 pi over 2. So next would be 5 pi over 2, which is the same as 10 pi over 4. So here's 5 pi over 2. And even if you didn't know what to label that, if you just kind of look at the pattern on the graph, right, you can see where the next point's going to end up, right? And you can, of course, see the next point would end up at 3 pi, right? And we keep going from there. But the critical part that I want you to pay attention to is this, okay? Let's basically make a rectangle encompassing one period of the parent. And that would be right here, okay? And then I'll make a rectangle encompassing one period of the transformed function. Right here. Okay? Now, this is what you want to notice. Looking at those rectangles, hopefully, if you look at the length of those rectangles, you can see how we've horizontally stretched the graph. Okay, and you can see where this value of b comes in. The period of the parent is 2/3, the b value, 2/3 that of the transformed. Vice versa, we've horizontally stretched the graph 1.5 times the length of the parent. So what's 1.5? Well, it's the reciprocal of b. In other words, if we take 1 over b, we can say that what we've done here is we've horizontally stretched the graph. First of all, because b here is actually less than 1. Because the key you want to notice just from basic fractions, if you take 2 pi and you divide it by a number that's less than 1, you're going to get a number that's actually bigger than what you started with, right? And that's why you're horizontally stretching with b less than 1. You know, it's the opposite of vertically stretching, where if we're vertically stretching, then A is going to be bigger than 1. If we're horizontally stretching, B is going to be less than 1. So B here is going to be 2/3. You can see that from the equation. And it's 1 over B, or 1 over 2/3, which is 3/2. It's reciprocal. That tells us by what factor we're horizontally stretching the graph. Okay? So the key here that we want to recognize is that we are horizontally stretching by a factor of 3/2, because the length of that period is 1.5 times that of the parent. Okay? It takes 1.5 times as long to reach 1 full cycle than it does for the parent. Okay? So if you need to, go back and pause and make sure you've absorbed what we've done. This is probably so far the most difficult part of the lesson, so you want to make sure you absorb it before you keep going. Okay? Focusing on the 2 different methods that I use to go from the parent x values to the transformed x values. One thing I want to mention before we continue on to the next problem is just, what would happen, for example, if we were given information backwards. For example, let's pretend that I was asked to write an equation given amplitude and period. Okay, so let's make it simple. Let's say I was given the amplitude was equal to 1, and let's say I was given the period was equal to 3 pi. So basically, just taking the problem that we have here and working backwards, because you'll notice we ended up with a period of 3 pi here. So remember that what we had learned initially, if you go back to the first page of the notes, we remember that we can change up this formula, that period is equal to 2 pi over b, but I can interchange these values. And of course, we can instead say that b is equal to 2 pi over period. So amplitude equals 1 tells me that a equals 1. So I have that for my equation. But I also need b, because remember the formula here is y equals a times sine of bx, assuming that we were told to write an equation for a sine function, okay? So to find the value of b, because I already have a, I just need b, I'm just going to say that to get b, I can say 2 pi divided by the period. So 2 pi divided by the period, which is 3 pi, and then if I just cancel, I'll get 2/3, right? And of course it works out because remember that's what we had right from the beginning here. So I'm basically just doing this example backwards. And so then I would write the equation y equals a, which is just 1 times sine of bx, 2/3 x. Okay, so that's just working backwards. And again, you'd be told write an equation, and I'll just add in here for sine. Okay, because we can also write equations, as you'll see soon, for cosine. All right, so let's move on here to example 2b, where we have an equation where we're going to find the period of y equals 3 sine of pi x, and then sketch the graph, okay? So step 1, we have to be able to draw the graph, we have to determine the amplitude in the period, okay? So we know in this equation we have y equals a sine of bx, okay? And this equation, you notice, looks a little different because the value of b is pi, right? Up here, the value of b was 2/3, but it can be pi. Pi is a constant value just like 2/3 is a constant value, right? So we're going to say that, of course, amplitude is equal to the absolute value of a, and of course a here is positive, so we can just say the amplitude is equal to 3. Okay, and we know that the period is going to equal 2 pi over b. Well, b here is pi, so that's 2 pi over pi. And so very, very simply here, the period is equal to 2. Okay, so in this example, for the first time, we're noticing that we have a period that's not written in terms of pi. But again, it doesn't matter, right? Pi gives us constant exact values, and so does just period of 2, a constant exact value. So if I want to find the 5 key x values for the graph, because I changed the period from 2 pi to 2, and keep in mind that pi makes a huge difference, right? For the period being 2 pi for the parent, 2 times pi is about 3, so the period is about 2 times 3 or 6, and now we've made the period 2. So the period is about 1/3 that of the parent now. Okay, so in this case, where you're going to see that we're actually going to be horizontally shrinking the graph. Okay, and again, we're going to use what we learned above. Remember, we learned above that when you're looking at whether you're horizontally stretching or shrinking, you're looking at the value of b. And we have a horizontal stretch when b is less than 1. And of course, pi is around 3, which is greater than 1. So in this case, we're going to have a horizontal shrink. All right. And you'll notice, of course, that b is greater than 3. Okay, so as you saw up here, we had a horizontal stretch by a factor of 3/2, which was a factor of 1 over b. And so here, we're going to be, when we graph it, we're going to be noticing, you can see here that b was equal to pi, right? So 1 over b is equal to 1 over pi. So we're going to have a horizontal shrink by factor of 1 over pi. In other words, like I said, 2 pi is about 6. This is 2. 2 is 1/3 of 6. 1 over pi is about the same as 1/3. Okay? All right, so let's look at the parent and compare it to the transformed graph. So again, we need to write the parent to help us write the table for the transform function and get the 5 key x values for the graph for the transformed period. Okay, so the parent here is going to be 0 pi over 2 pi, 3 pi over 2, and 2 pi, and 0, 1, 0, negative 1, 0. Okay, and if we then take the transformed graph, and notice this time, unlike for the example above, here not only have we changed the period, we've also changed the amplitude from the parent. So we're going to have to adjust the y values as well. Okay, so the simpler part of the transformation here, of course, is the amplitude. So what I can do, of course, is I'm going to multiply the y values of the parent by 3, right? So I'm going to have 0, 3, 0, negative 3, 0. Okay, now for the x values here, okay, in this case, remember I showed you 2 different methods of getting the x values. In this case, definitely the first method is the simplest, because watch, my period is 2 units. So I'm ranging in x values from 0 to 2. And it's so easy to split up 0 to 2 into 4 equal increments, right? So half of 2 is 1, half of 1 is a half, and then I'm just adding on a half each time, right? 0 plus a half is a half, plus a half is 1, plus a half is 1.5, or 3 halves, and 3 halves plus a half is 2. Okay, so that was very easy to just divide up into 4 equal increments. But of course, just to show you it works, the other thing to do, of course, is we can always divide the x values by pi, right? Because remember what we said, that when we're dividing the parent the period of 2 pi by b, that will give us the period of the transform function. So I can do the same thing, not only 2 pi divided by b, which is pi, but the other x values as well, right? So I could divide x values of the parent by pi, which is of course equal to multiplying by 1 over pi, okay? And of course you can check that, as an example again, right? So I can check that and I could say, well, watch, 3 pi over 2 times 1 over pi, canceling diagonally, 3 times 1 is 3, and 2 is in the denominator, and of course that gives me the 3/2 that I got, okay? But like I said, in this case, it's a lot easier to just go from 0 to 2 and divide it up into 4 equal increments and 5 key x values, okay? All right, so let's go ahead and graph the transform function, and we'll also dash the parent on there as a comparison, okay? So if I label the axis, so the axes, I've got 0, 1, 2, 3. I want to go up to 3 because of those y values, and -1, -2, -3. And the x-axis is going to range from 0 to 2. Here's 1, here's a half, and here's 1.5 or 3/2. Okay? So I've got 0, 0, and 1/2, 3, 1, 0, 3/2, -3, and 2, 0. Okay? And there's my sketch. Okay? And comparing that to the parent, let's look at the parent, okay? Now, at first glance, if I were to try to graph the parent, you might look at this and be like, well, how am I going to do that? These we see values that don't contain pi. What am I going to do? Okay? We'll just use some common sense, right? And we'll just do some approximation, right? Pi is approximately 3, right? 3.14. So let's just pretend that's about 3/2, 3 over 2. Okay, approximately, right? So if I were to graph the parent here, I've got 0, 0, and of course this line I think went off to the left a little bit. Of course, this graph is of course going through 0, 0 as well, the green line. Okay. Pi over 2. Well, pi over 2 is about 1.5, right? So let's go to 3/2 here, right? And so I've got, if I go over there to 1.5, which is about pi over 2, I'm at 1, right? So let me do this right here. I'll use red. So here's my, if I were to dash the parent here, now the question is, well, where do I go from there, right? So the next point is pi, which is about 3. Right? So basically the next point is at about 3, 0. Well, this graph ends at 2. So basically you're just going to continue and kind of head towards 3, 0 over there. And of course, this graph is just going to cycle normally, right? And it's going to have the same shape. It's just compared to the transformed graph, the period is going to be 3 times, because of that b value being about 3 pi, it's going to be about 3 times as wide as the transformed graph, right? Because again, the period of the parent is 2 pi, or 2 times 3, or 6, and the period of this transformed graph is 2. So this graph has been horizontally shrunk by a factor of 1/3. It is 1/3 as wide as the parent, or it's more specifically not 1/3, but 1 over b, or 1 over pi, right? And so I said that right up here. Horizontally shrunk by a factor of 1 over pi, okay? But also one more piece of information. So I'll write that, what we just said down there, right? Horizontally shrunk, there's a horizontal shrink because b is greater than 1. So when b is greater than 1, it's actually a shrink. And we said by a factor of 1 over pi. And remember, because of that amplitude being 3, we also have a vertical stretch, right? Because a is greater than 1. And that vertical stretch is by a factor of 3. Okay? So we have a horizontal shrink by a factor of 1 over pi and a vertical stretch by a factor of 3. Okay, so we're going to move on now to graphing y equals cosine of x, and we're going to see that all the techniques that we use to graph transformations of y equals sine x also apply to y equals cosine x. So we're going to start the same way that we did with y equals sine x. We're going to start with the unit circle and looking at the corner coordinates on the unit circle, right? So we know that here's the origin, and of course we have a radius of 1. And we know that the coordinate here where that radius intersects the unit circle is 1, 0. And here is 0, 1, negative 1, 0, and 0, negative 1. Okay, we also know that we're calling the measure of the angle in radians x, and the value of the cosine at that particular radian measure y. Okay, so remember that as far as these coordinates go, the x value represents the cosine of x, and the y value represents the sine of x. Okay, and that's true for all the coordinates on the circle, whether we're talking about these corner angles or the acute angles in between. Okay, I'm going to label the angles in radians. So we know here we have 0 radians, also 2 pi radians. Here is pi over 2, pi, 3 pi over 2, okay, and then 2 pi. And I can also label negative direction, right? So I've got 0 radians, negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. Okay, now this is where it might get confusing, so you have to listen very carefully, right? So you want to remember that as far as these coordinates go, and you can go back to remember why, go back a couple of sections in our notes from in the last couple of weeks, remember that the x value represents the cosine of x. So when we're looking to fill in the cosine values at each of these radian values, we're going to be looking at the coordinates x values. Okay? Don't let that confuse you, because when we're looking at y equals the cosine of x, y depends on x. So here, when we're graphing the cosine of x, that value of cosine x is actually the y value here. Okay? So we'll fill those in. We'll see that at negative 2 pi, the cosine of x is 1. At negative 3 pi over 2, the cosine of x is 0. At negative pi, negative 1, and so on. We're going to keep copying. Negative pi over 2, 0. At 0 will be 1, and so on around. And you'll be able to continue the pattern here. So you can see the pattern continues. 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1. Okay? Now, just like we did before for sine, to be able to have 5 key coordinates to be able to use for our parent, we're just going to focus on 0 and the next 4 positive radian values. Okay? And that will constitute the parent of all cosine graphs. Okay? And again, I'm going to make a sketch just like I did before. Okay? So, of course, here we have 0. In the y direction, here's 1. Here's -1. We'll go from 0 to 2 pi, 0 to -2 pi. Here is pi. Here's negative pi. Here is pi over 2. Here's negative pi over 2. Here is 3 pi over 2. And here's negative 3 pi over 2. Okay? And we will sketch the curve. So we've got negative 2 pi will be at 1. At negative 3 pi over 2 will be at 0. At negative pi will be at -1. At negative pi over 2 will be at 0. At 0 will be at 1. Pi over 2, 0. Pi, -1. 3 pi over 2, 0. 2 pi, 1. Okay? And here we go. Okay? Now, some of the features you want to notice here is that between 0 and 2 pi, if you look at the shape of this graph, you're looking at basically one big valley. Instead of a hill and a valley between 0 and 2 pi like sine function, here we have one big valley. Okay? Another thing to notice, if we look back here at the sine function, you notice that at 0, it's starting at the midline, right? And here, on the other hand, for cosine, at 0, we're starting at the maximum, okay? So as a note here, for y equals cosine of x, between 0 and 2 pi looks like one big valley. Okay? And you'll notice this, it's important to recognize the difference in shape because one of the practice tasks you'll have to do when you do the Pearson Realize assignments is to be able to graph using their tools, and you'll be able to pick, a general cosine graph and it'll look like a big valley, and then you'll also be able to pick a tool for a sine graph and it'll look like a hill in a valley. Okay? All right, so as you'll notice here, if we were to make the same sort of rectangle that we did before, going from a max to a max, it's very easy to do here. We can see that'll represent one period. So you can see again for y equals cosine x, just like for y equals sine x, the period is equal to 2 pi. Also, you can see here, the amplitude, of course, is the distance between the midline, which the midline, of course, is still at y equals 0. Okay, so we still have the midline at y equals 0. And the amplitude, which is the distance from the midline to the max or the min, is 1 unit. Okay, so the amplitude is equal to 1 unit, just like for the sine parent function. We're going to use the same variables, represent amplitude, absolute value of A, and the period is going to be 2 pi over B. Okay, and of course, vice versa, I can write this as an equation. Vice versa, if I were trying to find the period from a given value of B, I could instead say B is equal to 2 pi over the period and be the same thing. Okay? All right, so let's look at actually doing an example with some transformations in it. Okay? So we're going to sketch a graph of this particular cosine curve, and we're going to find the amplitude and the period of y equals -2 cosine of 4x. Okay? So to be able to do this, we're first going to determine the amplitude and the period. Okay, so notice, of course, this is important, that in this case we have a reflection. Okay, so A is actually equal to -2. And we know that the amplitude is equal to the absolute value of A. So we have to take the absolute value of -2, which is equal to 2, and that's the amplitude. Because remember, the amplitude is always positive. Okay? In order to be able to get the period, remember we have to look at the value of B. And we can see here, I'll even write the formula underneath, A cosine of B times X. We can see that B here is equal to 4. So the period is going to equal 2 pi over B, or 2 pi over 4, of course. And just, that's simple to simplify. 2 goes into 4 twice. And so the period is actually pi over 2. All right. And so you're going to notice here, of course, the period is smaller than the period for the parent. The period of the parent is 2 pi, and this is only pi over 2. And so the parent graph is actually has a period 4 times that of this graph. Or in other words, this graph has a period that's 1 over B, or 1/4 as wide as the parent. And so we have a horizontal shrink here. Okay, and since I have room, I'll write that down here, right? So we notice here that B is 4, so B is greater than 1. So we have a horizontal shrink, and that horizontal shrink is by a factor of 1 over B, or 1/4. Okay? Another piece to notice here is that the absolute value of A is greater than 1, right? Because the absolute value of A is 2. So we have a vertical stretch by a factor of 2. Okay, and one more piece to notice is because of that negative, we have a reflection over the x-axis, right? So we have a reflection over the x-axis. And those features we picked out right from the equation even before graphing. Okay? All right, so we're going to need to find 5 key x values because we did change the period from what it was in the parent because of the value of B not being 1. Okay? So the parent has this table, of course. Now be careful, make sure you use the parent table for y equals cosine x and not y equals sine x. You always have to pay careful attention to whether you are doing a cosine or a sine problem, because you don't want to use the wrong parent, because then you'll make mistakes on your graph. So in this case here, remember, you're using these 5 key values for your parent. Okay, so we've got 0, pi over 2, pi, 3 pi over 2, and 2 pi, and 1, 0, -1, 0, 1. Okay? Now, for your transformed function, okay, and that was y equals -2 cosine of 4x. Because we changed the amplitude and we reflected and we also changed the period, we're changing x and y compared to the parent, okay? And again, the easier values to change are the y values. So we're going to multiply the y values by -2, right? And so 1 times -2 is -2. 0 times -2 is 0. -1 times -2 is 2. 0 times -2 is 0. And 1 times -2 is -2. Okay? Now, for the x values here, remember the period is pi over 2. So remember, we've got 2 different ways we can do this. One is split this up into 4 intervals. So 0 to pi over 2. Okay, I know that half of a half is a fourth, so halfway I'm at pi over 4. I also know that half of a fourth is an eighth, so halfway would be pi over 8. Okay, I also know that each time I'm adding 1/8 of pi. 0 plus 1/8 of pi gives me the 1/8 of pi, pi over 8. Plus another eighth gives me 1/4 of pi, right? So if I add another eighth, 1/4 is the same as 2/8 plus another eighth is 3/8. So I have 3 pi over 8 here. Okay, and it's this value is the one that a lot of students will make mistakes on, and so it sometimes does help to do the other method to get these values. Okay, and the other method, of course, is just like we divided 2 pi by 4, the value of b, to get the period. I can do the same with the other x values, right? So the other way to do it is, or I can divide the x values by b, which is equal to 4, okay, which is the same as multiplying by 1/4, okay? And I'd still get the same values, right? So 2 pi times 1/4 would be 2/4 or 1/2 pi, right? 3/2 times a fourth is 3/8 pi, and so on. So I could do it that way if I wanted to, right? And again, if you want to see an example of that, take the 3/2 as an example. 3 pi over 2 times 1/4 certainly does give me that 3 pi over 8. So that is another way to get there. And the one thing you'll notice here that's different than what we've done before, anytime during this year with any other types of functions, whenever we changed x values, it was always in a horizontal shift. So we were always doing addition or subtraction when we changed x values from a parent to a transform functions. And this is the first time where we're doing multiplication or division to change x values. So that's something you want to notice as well. Okay? All right, so let's go ahead and graph. So we have for the transform function, I'm going to transform the graph by going from 0 to pi over 2, the period. And half of the pi over 2, of course, is pi over 4. Half of pi over 4 is the pi over 8. And then, of course, adding on another pi over 8 to pi over 4 gives me 3 pi over 8, right? And since I'm going up to 2 and down to -2, I'll put that on the y-axis, okay? So I'm starting here, 0, -2, pi over 8, 0, pi over 4, 2, 3 pi over 8, 0, and pi over 2, -2, okay? And so a couple things you want to notice here, okay? One is that we've reflected this graph, right? So here we had one big valley, but of course here where we're reflecting, going from 0 to one whole period, we have reflection gives us one big hill. Okay, that's how cosine is going to look. Going from 0 to the first period of the graph, assuming, of course, there's no shift left or right, which is what we're going to be looking at next on the next page. Going from 0 to the first period, you're going to see that one big hill there. Okay? Another piece to notice here that I wanted to mention just about just design of the cosine graph compared to the sine graph as well. Is just the fact that we have an axis of symmetry here of the y-axis. You'll notice we have like kind of almost like the W shape that you see when we were looking way back when we were doing polynomial functions, degree 4 functions, you remember that W. Or with quadratic functions, a parabola, you remember the U, and that these are symmetric about the y-axis. And we learned that graphs that are symmetric about the y-axis, where they could basically be folded onto themselves over the y-axis, are called even functions. Okay, and if we compare that, remember, to the sine graph, remember when we were looking at the sine graph, we had said that the sine graph was an odd function because if I rotated it, remember, we rotated it upside down. Here it is, rotated upside down. It looks identical to what it did right side up, okay, because it had rotational symmetry about the origin. And you'll notice, for example, if you look at negative pi over 2, its y value is the opposite that of the value at pi over 2. Well, comparatively, if you look at cosine, on the other hand, at negative pi over 2 and at pi over 2, you have the exact same y values at negative 3 pi over 2 and at 3 pi over 2, and so on. Okay, in other words, what you'll notice here is that cosine is an even function. Okay, because it's symmetric across the y-axis. Okay, and what that means in sort of technical terms is that if I calculated, the value of the function at a specific negative value, like negative pi over 2, it would equal the same value at the positive x value that corresponds. So that means that f of negative x has to equal f of positive x. Okay? So of course, what that means for our graph down here is that if I were to continue this graph over the y-axis into negative values of radian measures, I would have another hill over here that would be identical to this hill, okay, because it's an even function. All right, so before we just finish this problem up, let's just look at the parent graph against this graph, okay? So I'm just going to dash the parent graph. I've got 0, 1, okay? Pi over 2, 0, okay? So pi over 2, 0. Well, here's pi over 2. Here's 0. And you'll notice, as far as on our graph as it's scaled now, that's all we can fit. Okay, so you don't even see the rest. Obviously, this function will continue and you'll see the waves on it if we were continuing farther along, but that's the only portion of the parent function that we can see on here, because that function, the parent function, is much wider than this function, because this function, remember, is horizontally shrunk and is 1/4 as wide. This period of pi over 2 is 1/4 the period of the parent, which is 2 pi. Okay? So as I said before, it is extremely important to label your axes carefully, because otherwise you can't tell what you've graphed. The graph for the particular equations only match up if you label the axes carefully and you know what the points correspond to. Okay? One thing I want to mention before we go on to shifting graphs left, right, up, and down is to just look at the general pattern of cosine in a similar way that we looked at the general pattern of sine. Notice that between 0 and 2 pi, or basically in the first period of the graph starting at 0, as long as the graph isn't shifted left or right, up or down, you'll notice that we start at the max, then we go to 0, then we go to the min, then we go to 0, and then we go to the max. So basically the pattern here for cosine is max, 0, min, 0, max, okay? And you can compare that if you go back a couple pages on sine, we had done the same thing, looked at the pattern for sine. And of course, the same is true when we look at the reflected graph, okay? So of course, this graph was reflected. Of course, we changed the period also. The period was pi over 2 instead of 2 pi, but as long as the graph isn't shifted left or right, as long as we're starting at 0, the same principle is going to apply, okay? So reflecting here, what happens is we go from the min to 0 to max to 0 to min, So with the reflection, we have min, 0, max, 0, min. And that's just a general pattern that you want to notice. Okay, so let's move on now. And we're going to look at some formulas here that look, again, with H and K, very similar to formulas that we have used in the past. Okay, and these formulas will help us to translate the graph left and right by using the value of H, and up and down by using the value of K. Okay, so the amplitude is still going to be the absolute value of A for both sine and cosine, just like it's been even when we weren't involving H and K. The period is still going to be 2 pi over B. Now, for the midline, because we're shifting the graph up and down now, the midline is no longer necessarily going to be y equals 0. Because shifting up and down depends on the value of K, the midline is going to be y equals K. Because before, of course, without K being there, K was 0, and the midline was y equals 0, the x-axis. Okay? So y is equal to K is going to be the midline. All right? So we're going to be, in this example, comparing the graphs of vertical and horizontal shifts. And something you want to be particularly focusing on too is that a horizontal shift is typically called a phase shift. Okay? And part of the reason for that is, like, for example, the moon is, the pattern of moon would be like in cycles, right? Moon and tides and so on. And so you have phases, like phases of the moon. And so that's one of the reasons why we call this a phase shift, because in practical terms, the sine and cosine functions can model practical situations that would involve phases. Okay? So what we're going to look here at is what happens, how we can easily shift the graphs up, down, and left and right. Okay, and in some cases we can easily do this without even using a table, and you'll see how that works. Okay, so for example here, let's look at the parent function here, y equals sine of x. Okay, and if we remember just looking at parent values, you'll notice here that we also put in some values on the negative x-axis too. So I'm going to include some negative radian values as well. So we've got 0, and over here I'll make this 2 pi, and here's pi, and pi over 2, and 3 pi over 2. Okay, and also, since we're moving a little bit to the left, I don't have room for a whole period to the left, but I'll do negative pi over 2 and negative pi. Okay, so just plotting the values that we know for the sine curve, we know that at least for the 5 key points that we're normally using for 0 and positive, we know that when x is 0, the sine of 0 is 0. When x is pi over 2, the sine of pi over 2 is 1. And I'm going to go ahead and label the graph. I didn't do that yet. So we've got 1, 2, 3, 4, 5, negative 1, negative 2, negative 3, negative 4, negative 5. So here's pi over 2, 1, pi 0, 3 pi over 2, negative 1, and 2 pi 0, and just continuing the pattern. I mean, you can just kind of see what the pattern is here. You can continue it here at pi over 2, we're at negative 1, and at negative pi, we're at 0, right? And I'll just draw that curve in. Okay, so the nice thing about doing just vertical shifts or just horizontal shifts is that we can actually move the graph up, down, left, and right without actually having to make a table. Okay, so, for example, to do y equals sine of x plus 3, I could make a table. And we know from past experience, because here k is equal to 3, that would mean that we're going to add 3 to the y values of the parent. But what would be a simpler way to do it, or we can simply move points of the parent up 3. Okay, and so that's the simplest way to do it here. Now, as long as there's no horizontal stretch or vertical stretch or shrink, it's actually quite simple to do this. Okay, so basically, all we need to do is just move every point up 3. So I can take this point and count 1, 2, 3, 1, 2, 3, 1, 2, 3. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, and so now for this graph that's been transformed by moving up 3, I can see the amplitude is still 1. The amplitude stayed the same. We didn't shift left or right. We didn't reflect. So it's not vertically stretched or shrunk or reflected. The period hasn't changed. Everything stayed the same except the midline has changed. Okay, so it's important to recognize the midline for the parent was at y equals 0, right? Because k up here was 0, right? So that's important to recognize. K is equal to 0 here, right? Because plus k, there is no value there. So k is just 0. Where here, k is equal to 3. So we set up here, the midline is y is equal to k. So for this graph, the midline is y is equal to 3. And so I could draw that midline in there. Right here. Okay, and it's something else to notice here, if I were told, for example, that I had a graph where the midline was 3 and I knew the amplitude is 1, I could just add 1 to that midline to get to the max. 3 plus 1 is 4, and subtract 1 from the midline to get to the min. 3 minus 1 is 2. Okay, and I did that much more simply than taking time to make a table. Okay, we can do the same thing with cosine. Okay, so for cosine, if we label the graph in the same manner, we've got the 0, the 2 pi, here is pi, pi over 2, and 3 pi over 2, and negative pi over 2, and negative pi. Okay. And just remember, starting with our 5 key values, when x is 0, the cosine of 0 is 1. When x is pi over 2, the cosine of pi over 2 is 0. The cosine of pi is negative 1. The cosine of 3 pi over 2 is 0. And the cosine of 2 pi is 1. Okay, there you have that U shape, that valley, right? And then if I just continue the pattern, of course, at negative pi over 2, because this is an even function, it's going to have the same y value as at pi over 2. And at negative pi, you're going to have the same value as at pi, right? So there's the y equals the cosine of x. So now with y equals cosine of x minus 2, again, I could make a table, or just remember here, basically I'm shifting the graph down 2. Okay, so keep in mind, over here we had a vertical shift up 3. Okay. Another way to describe that vertical shift, I could sometimes you'll see it this way. Sometimes, for example, in your assignment, they'll say, what's the vertical shift? And so we can just say the vertical shift, because you're moving up, it's a positive 3. So we could just say the vertical shift, and I'm just abbreviating that VS, is going to be positive 3. Okay? And so moving over here, what we have is a vertical shift down 2, okay? And again, sometimes you might see it like this, a vertical shift down 2, meaning of -2. Okay, so again, you might see that. They might ask you to type in on your assignment a vertical shift as simply, either in words saying it down 2 or writing it as -2. It means the same thing. Okay, so I'm going to move all the points of this graph down 2. So I'll just say 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. And so there I have a vertical shift down 2. Okay, so key thing to notice here is that these two sine equations, these two cosine equations. So what happened in both of these cases is you were dealing with a vertical shift. Okay, down here, we're going to be looking at horizontal shifts, okay, for these 4. And horizontal shifts, again, another word for that is a phase shift. Okay. So let's look again for y equals sine of x. I'm going to basically duplicate what I had here, only this time when I do the addition or subtraction, to be able to move the points, I'll be moving the points left and right instead of up or down, because what I've got here is sine of x plus pi over 2, which means that I have a horizontal shift left pi over 2, because remember, for values of h, we take the opposite here. Okay, so what we have is a horizontal shift left pi over 2. Okay, and another way of saying that is just hs is equal to negative pi over 2. Okay, so I'll graph the sine function, the parent sine function, just as I did before. So I've got 0 to 2 pi, and here's pi and pi over 2 and 3 pi over 2. You'll do this so much, you'll get used to just doing it very easily. Negative pi over 2 and negative pi, right? And I could literally, without even thinking about it, just copy what I had up here, right? So I'm just going to go ahead and do that. And I'm going to label here 1, 2, 3, 4, -1, -2, -3, -4. Okay? So here's the parent sine function. Okay, now what I'm going to do is I'm going to either shift all the points left pi over 2, or again, another option is I could make a table and I could subtract pi over 2 from the parent x values, right? Or, which is what we're going to do here, move points of the parent pi over 2 to the left. Okay? So I'm going to look at all the points here. Now, obviously, for this point here, I don't have room to move it pi over 2 to the left. But I'll take this point and I'll move it pi over 2 to the left. So pi over 2 minus pi over 2 is negative pi, right? And then I'll take this point here. I'll move it pi over 2 to the left. And this point, pi over 2 to the left. And this point, pi over 2 to the left. This point, pi over 2 to the left. And this point, pi over 2 to the left. Okay, and so when I draw this graph, you can see how very easily, if you compare the red graph to the purple graph has been shifted pi over 2 units to the left, okay? So it's a phase shift. They're basically out of phase with one another, okay? So let's do the same thing for cosine. So I'm just going to color code this for you. Okay, so you can see here we did sine shifting up and we did cosine shifting down. And so here, just to change things up here, we did sine shifting left. Here we'll have cosine shifting right. Okay, so again, we're going to use that same parent that we used up here in red. And literally, I can just do the copying here, right? So I've got 0 to pi, pi over 2, 3 pi over 2, negative pi over 2, and negative pi. Okay? And so here are my points. Okay, so there's the parent, and you'll notice here what we have is we have a phase shift right pi over 3, right? So we have a horizontal shift right pi over 3. Another way of saying that is just horizontal shift is positive pi over 3. Okay? So that means, again, I could either move my points to the right pi over 3, or I could make a table and add pi over 3 to the x values. Okay? Now, at first glance, you might wonder, and I'll zoom in a little bit on this, I think. You might wonder, how am I going to move these pi over 3 because, I don't have my graph labeled in terms of thirds of pi. I have them labeled in terms of halves of pi. Well, think logically here, right? A third is in between a quarter and a half, right? So here's a quarter, here's a half, right? A third is going to be a little more than a quarter of the way, basically from one point to the next. So if here's negative pi, if I go pi over 3, it's not going to be quite pi over 2. It's going to be a little over pi over 4. So it'll be about here. And we just kind of approximate it, right? And so I'm going to do the same thing here. A little more than pi over 4 would be pi over 3. A little more than pi over 4 would be pi over 3. Same thing over here. Same thing over here. Same thing over here. Okay? And so I can just sketch my graph here. And there I go. Okay, and so you'll notice again, you can see the purple graph in phase is just a little bit to the right of the red graph. Okay, and so again, you can either do that by using a table or by just moving the points to the right pi over 3. If you use a table, then you would just be adding pi over 3 to the x values. Okay, so we're going to finish up today by graphing a function that has a combination of types of transformations here. Okay, so you'll notice here we've got y equals a times the sine of b times x minus h plus k. So you want to look at the situation here and figure out the value of the amplitude, the period, the vertical shift, and the phase shift. In other words, the horizontal shift as well, to be able to figure out how to make the table to create the graph. Okay, so first of all, notice that the amplitude is going to equal the absolute value of a, but a is positive here, so a is equal to 2. The period, we can figure out here, you'll notice that to the left of x, or basically to the left of the parentheses here, we don't see a number, which means that b is understood to be 1 here. So if I want to calculate the period when b is 1, the period is the same as that of the parent. The period is simply 2 pi. Okay? There is a vertical shift here because you can see that k is equal to -2, which means, of course, that the midline of the graph is at y equals -2, which means altogether here that there's a vertical shift, and that vertical shift is down 2. And another way of expressing that, of course, would just be -2. If you were asked for it, for example, in your assignment, what's the vertical shift? Sometimes they'll ask for it in words. Sometimes they'll ask for it as just simply a number, okay? The horizontal shift, otherwise known as the phase shift, is based on the fact that h here is equal to pi over 2. And so we can say that there's going to be a phase shift right pi over 2. Or another way of saying that is simply pi over 2. It's because it's positive, so you might just have to type it in as simply pi over 2. So whereas before, on the prior page, we were shifting left, right, up, and down by simply counting and not using a table, here, when you have a combination of both a phase shift, a vertical shift, and a vertical stretch, you probably want to use a table to be able to get the accurate points, okay? So I'm going to show you how you can do that for this particular situation. So we're going to find 5 key x values for the graph, okay? We're going to start with using the parent and then transforming the parent, okay? So for the parent, which is y equals sine of x. So pay attention, we're back to sine. Again, you've got to pay attention to whether you're dealing with sine or cosine, so you use the correct points. So looking at that parent, we're going to start at 0 and go to 2 pi, right? So we have 0, pi over 2, pi, 3 pi over 2, and 2 pi, and 0, 1, 0, -1, 0. Okay, so for the transformed function, and again, that equation is going to be y equals 2 sine of x minus pi over 2 minus 2, okay? We are going to make a table based on the information that we have here, okay? So first of all, we know that for the y values here, they're going to be affected by the amplitude and the vertical shift, okay? And just like we've done before, we always consider the multiplication first and then the addition or the subtraction. So for the y values, we're going to first multiply y by 2, and then we're going to subtract 2, okay? So if I multiply 0 times 2 is 0, minus 2 is -2. 1 times 2 is 2, minus 2 is 0. And again, for 0, we'll get the same value again, -2. For -1, -1 times 2 is -2, minus 2 is going to be -4. And again, for 0, we'll get the same value, -2. Okay, so those are the y values. Now, for the x values, remember what we said. On the prior page, we just moved points. But we can't do that here because of that, the fact that we also have that vertical stretch going on. So that's going to affect where the points go. So instead, what we're going to do is we're going to take care of this horizontal shift, this phase shift, by adding pi over 2 to the x values, okay? So we're going to add pi over 2 to x, okay? And so 0 plus pi over 2 is going to be pi over 2. Pi over 2 plus pi over 2 is going to be pi. Pi plus pi over 2 Well, 1 plus a half is 3 halves. So we have 3 pi over 2. 3 pi over 2 is the same as 1.5 plus another half of pi gives us 2 pi. 2 pi plus another half of pi is 2.5 pi, or 5 halves pi. Okay? So you have to do some addition to be able to get there. Okay, and you have to be really careful. You know, when we're doing a phase shift, we're doing addition or subtraction to the x values. When we were changing the period, one of the options we had was multiplying or dividing by the x values. So you want to just look at that and distinguish between a phase shift and a period change. Okay, a period change changes how wide the graph is or how long it takes to go through a cycle, whereas a phase shift shifts the graph left and right, but doesn't change the period. Okay? All right, so what we're going to do here is we're going to graph this, and first thing I want you to notice here is even though we're starting at pi over 2, the period is still 2 pi. Remember, we didn't change the period from the parent, because if you add 2 pi and you add another half of pi, you get to 2.5 pi, which is 5 pi over 2. So from pi over 2 to 5 pi over 2 is still 2 pi. It's just shifted right pi over 2, which is what the phase shift does. Okay? So what I want to do is I want to scale my graph to be able to fit these points on it. And I have a choice. I could either scale my graph using 0 to 2 pi, or I can scale my graph using the transform values. So I'm going to use the transform values here because then I know I'll be able to see one full period of the transform graph on my graph. All right, so notice here, I do still want to start my graph at 0. Okay, so I'm going to start my graph at 0. And then I need to be able to get to at least 5 pi over 2. So 5 pi over 2 is 1/2 of pi less than 3 pi. And what I'm figuring is that if I divide into pi over 2 increments, I'll be able to fit everything. Because watch, pi over 2, pi, 3 pi over 2, 2 pi, then 2 pi and another pi over 2 is 5 pi over 2, and then another pi over 2 is 3 pi. So if I break this up into increments of pi over 2, I can fit my values. So I'll make this 3 pi, okay? And then I'll just count. Here's pi over 2, here's pi, here's 3 pi over 2, right? Because pi over 2, 2 pi over 2 is pi, 3 pi over 2, 4 pi over 2 is 2 pi, 5 pi over 2, and 6 pi over 2 or 3 pi, okay? So I'm going to also label my axes to make sure I can fit all my points. I see I go down to -4, so I'm going to label the axes such that I can fit 1, 2, 3, 4, -1, -2, -3, -4. Okay? Now I'll graph the parent, and then I'll graph the transformed function. Okay? Or actually, I'll do the transform function first, and then we'll do the parent. So we've got pi over 2, -2, pi 0, 3 pi over 2, -2, 2 pi -4, 5 pi over 2, -2. Okay? Now, when I notice here, I don't have points here at the end, and I want to continue my pattern here, right? So the key to keep in mind here is that, remember, because k is -2, that's the midline. So I'll go ahead to try to use this as a guideline to figure where I'm going here. Watch, here's my graph. Okay, and so basically I can figure, remember the general pattern for sine, I've got to come down here and then I'm going to go up to here at 3 pi, right? And then it'll continue. So even though these additional points aren't on the graph, this way I've filled up my graph, you know, and not just cut off the sine curve. I mean, it wouldn't be wrong if I put an arrow right here after this point, it would still work, but it's nice to fill the graph in. And if I just remember the general pattern of the curve, I can fill these other points in. Okay, because remember, you remember the general pattern. You know, if we're shifting to the right pi over 2. So here's our 0, max 0, min 0. And then I keep going, right? And here's 0. And then, of course, here's the min. So it's just, the pattern just continues. All right? And so now I'm going to dash the parent function in here. So as a comparison, so I've got 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, 2 pi 0, okay? And of course, again, you know, I can continue this, so I've got my graph filled in, right? Because I've got 0, max 0, min 0, max 0, right? And so there's my parent. And so you'll notice here, you can see how in the phase, the green graph has been shifted pi over 2 to the right, right? So we have a max here at pi over 2. The max of my transformed graph is at pi, right? And same thing here. Like for example, here I've got right here in my transformed graph, I have a min here, right? And if you kind of look at the parent graph, it will be at the min at pi over 2 to the left of that. You just can't see it because it's off the graph. Okay? All right, so we've gone through looking at graphing sine and cosine, and we've looked at how the amplitude, the period affect the graphs. We've also looked at vertical shifts and horizontal shifts, and the horizontal shifts are also called phase shifts. So we've done quite a lot, and you probably want to go back and review and pause and try to make sure you're understanding everything in order to be able to do the assignment. Okay? Have a great day.